Hi, I'm Dr. Renugar. In this session, I will continue with deadlocks. Let's start. Deadlocks can be described more precisely in terms of a directed graph, which is known as resource allocation graph. Now, this graph consists of set of vertices and set of edges. The set of vertices is partitioned into two different type of nodes. This P set consists of all the processes in the system. Okay, these are all active processes in the system. And the another is R. It consists of the all resource types in the system. Okay, a direct edge from P1 to RJ, it is defined as a request edge. This edge means P1 has requested a resource type RA and it is currently waiting for that resource. Here P1 is waiting for RA. Okay. A directed edge from resource to process. This type of edge is known as assignment edge. This edge means an instance of type RA has been assigned to or it is held by P1. In resource allocation graph, a process is represented as a circle. Any resource, suppose the resource is RJ, it is represented as a rectangle box. Now in this case, there are 4 instances of RJ. Means if suppose RJ is a tape drive, then currently system has 4 tape drives. Okay, these are the 4 instances. And this is how we represent that process PI has requested for an instance of RJ. This is yes request edge. Now PI is holding an instance of RJ means one of the instance of RJ has been allocated to PI. So this edge has now become assignment edge. This is an example of resource allocation graph. In this example, the sets P, R and E are defined as. Now how we will define P? P is the set of active processes. So according to the diagram, it is P1, P2 and P3. The set R is defined as, can you see the number of resources? Yes, R1, R2, R3 and R4. So this is a set R. Then there is another set which is E. E is a set of edges. Now there is an edge from P1 to R1. This is a request edge. P1 has requested for an instance of R1. Then there is an edge from R1 to P2, means R1 has been allocated to P2. This edge is assignment edge. This is request edge, assignment edge. Then similarly, we can write down all other edges. P2 to R3, this is request edge. Any edge from process to resource is a request edge. From R3 to P3, sorry, like this, R3 to P3, this is assignment edge. Then R2 to P1 is assignment edge. R2 to P2 is again an assignment edge. Okay. So this is the set of all edges in this particular resource allocation graph. Now number of instances. We are currently understanding that how to interpret this resource allocation graph. Number of instances of R1, 1. As you can see, there is just one dot. So R1 has just one instance. R2 has, simply count the number of dots. It is 2. R3 has number of instances 1. And R4 has Number of instances 3. And if we talk about states of process, so what is the current state of P1? P1 is holding R2 and waiting for R1. Clearly, I hope you are able to understand this. P2, yes, state of P2 is holding R1 and waiting R3. P2 is holding R1 and R2. It is holding R1 and R2 and it is waiting for R3. Okay. So let's see state of process P3. P3 is holding R3. So this is how we interpret a resource allocation graph. The question is the system is in deadlock? Now we will identify the cycles in graph. Can you draw cycles in graph? As you can see, P1 to R1 there is an edge. From R1 to P2 there is an edge. P2 to R3, R3 to P3, then P3 to, yes, R2, and then R2 to back P1. There is this is the first cycle that I am able to identify. Is there any other cycle that you are able to identify? Yes, we are, which is this cycle. Okay, this one. And one was this outer cycle. So let's talk about inner cycle. It is P2 to R3, R3 to P3, P3 to R2, and again R2 to P2. So these are two minimal cycles that we are able to identify in our system. So it means that there is a circular weight in this graph. There is a circular weight. P1 is waiting for process P2 to finish. P2 is waiting for process P3 to finish. And P3 is waiting for process P1 to finish. So in between processes, the circle is like this. For the first cycle, it is like this. And for second, we can see P2 is waiting for P3 and P3 is waiting for P2 to finish. So processes P1, P2 and P3 are deadlocked. Let's now take another example. In this example, there is also a cycle which is very clearly visible, but let me draw. The cycle is P1 to R1, R1 to P3, P3 to R2, and R2 to P1. Okay. Then there are two other edges in this graph, resource allocation graph, R1 to P2 and R2 to P4. These both are assignment edges. Okay, these are assignment edges. And what are the states of P1, P3, P2 and P4? P1 and P3 are in waiting states. They are waiting for each other to finish the execution. Okay, but P2 and P4 are not waiting. As per graph, they are not waiting. They are holding the devices. So it is possible that P2 or P4 release R1 and R2. So it is possible that P2 releases this resource R1. This R1 will be now available to P1 and the cycle will break. Other option, P4 may release this instance of R2 and this instance of R2 may be allocated to P3 then and the cycle will break from here. So cycle can break from here or here depending on if P1 release R1 first or P4 releases R2 first. So in this way, the cycle exists, but yes, there is no deadlock. Sometimes we say that there was cycle, so there is deadlock. And in next example, I say there was cycle, but there is no deadlock. So what is the conclusion? The conclusion is, if the graph has no cycle, no deadlock. But if the graph has a cycle and there is only one instance per resource, then definitely there is deadlock. If there are several instances of resource, then there is possibility of deadlock, because these several instances may be allocated to some other processes which are not waiting, which are not waiting. So there is possibility they may or may not be waiting. If they are all waiting for each other, then there can be deadlock. But if the processes are not waiting, then there will be just a possibility of deadlock, but no assurity of deadlock. I would recommend you to go back to the previous slides and plot the cycles on your own and try to understand these two conclusions. This was all about resource allocation graph. I hope you understand. Thank you.